If you wanted to build and run an application a few decades ago, your first step involved real estate. You had to purchase physical mainframes and house them in acres of climate-controlled rooms. Even as computing evolved into on-premises data centers, the physical reality remained demanding. Keeping these machines online required sysadmins to battle an endless tangle of cables, manually replacing failing hard drives and monitoring power supplies at all hours of the night. Eventually, the cloud arrived, offering virtual machines. We didn't have to touch the hardware anymore, but developers were still chained to the operating system. They spent their days applying security patches, updating runtimes, and configuring load balancers to distribute traffic. This graph shows a standard application's traffic over time. Notice this massive sudden spike. Maybe it's a flash sale or a viral post. To survive that one brief moment without crashing, traditional servers must be permanently scaled up, creating a massive gap between what capacity is available and what is actually being used on a normal Tuesday. That gap represents idle capacity. Companies end up paying top dollar, 24 hours a day, 7 days a week, for expensive compute resources that spend the vast majority of their time doing absolutely nothing. When we force highly skilled developers to spend up to 40% of their working hours maintaining infrastructure instead of writing new code, the inefficiency of the model becomes clear. To fix this, the industry moved toward a concept called serverless. The name is a misnomer. The physical hardware still exists. What vanishes is your obligation to manage, patch, or provision it. This diagram maps the traditional shared responsibility model. In a standard setup, the cloud provider handles the physical hardware and virtualization layers at the bottom. You, the developer, are responsible for managing everything on top: the operating system, runtimes, code, and data. In a serverless architecture, the boundary of responsibility pushes up. The cloud provider absorbs the operating system and the execution environments. All that is left for the developer to manage is the application code and data. That heavy lifting doesn't disappear. It gets absorbed by companies like Amazon, Google, and Microsoft. They operate these massive data centers at an industrial scale, applying global security patches and balancing hardware loads behind the scenes. By trading granular control over specific server configurations for convenience, the developer is freed from the operational maintenance of the underlying infrastructure. The compute engine powering this serverless ecosystem is known as Function as a Service, or FaaS. Function as a Service relies on event-driven execution. Instead of an application running constantly in the background, you write small, modular pieces of code. These functions sit dormant until a specific event triggers them, like a user clicking a link or a photo being uploaded to a database. The exact millisecond that event occurs, the cloud provider wakes up, instantly allocates a runtime container, executes your code, and delivers the result. This creates a highly elastic environment. If thousands of users suddenly upload photos at the exact same time, the platform instantly spins up thousands of concurrent, identical instances of that single function to process them all simultaneously. And as soon as the tasks finish, those resources spin down and disappear. You are billed exclusively for the exact milliseconds your code was actively executing. Compute power becomes a true on-demand utility. You pay for a taxi only while actively sitting inside it, instead of buying, fueling, and repairing an entire fleet of cars that sit unused in a parking lot. A system that scales all the way to zero does come with specific technical constraints. The most prominent is known as a cold start. When a function has been completely dormant for a long period of time, the cloud provider deallocates its resources. The next time it gets triggered, the provider has to boot up a brand new container from scratch. This initialization process creates a brief, noticeable latency delay before the code actually runs. The second major constraint is statelessness. Once a serverless function completes its task and spins down, it forgets everything about the transaction it just processed. It holds no local memory. To retain any permanent memory or track a user session state, developers must write their functions to push data out to external, managed databases, often called Backend as a Service. Because of these latency and state constraints, you cannot simply drop an older, monolithic legacy application into a serverless environment. Taking advantage of this model requires a strict architectural rethink from the ground up. For modern, event-driven workloads, Moving beyond the server represents a total departure from traditional software engineering. When teams no longer have to worry about provisioning hardware, the business benefits compound quickly. Companies can build prototypes faster, iterate on user feedback almost immediately, and radically reduce their computing costs. The heavy lifting of system administration, load balancing, and security patching has been successfully outsourced to the cloud giants who specialize in doing it at scale. This means developers can stop worrying about infrastructure and focus 100% of their energy on writing the application logic that delivers value to their customers.